Probably Sean Connery's probably the best James Bond there ever was.
That's where you made it more. The homework wasn't posted on there, was it?
Hmm?
The homework wasn't on Moodle, was it? Yeah.
Binary search?
Was it dude?
Yeah.
Yeah. Was it good? I sworn it wasn't dude.
No. That's why I was up at 4 o'clock in the morning doing it.
Oh, you're up at 4 o'clock?
Yeah.
Okay.
When it was turned in, like in at like 4:26.
Oh, okay. Well, let's start with that today. Let's start with binary search, and then we'll move from there to local variables and parameters, okay? All right. So let's start with binary search. Yep. Right. A few minutes ago. Oh, I should say 1 minute and 12 seconds ago. All right, so here's the starting point. And let's make a folder for today, just in case we want to keep it. How many people still kind of remember what we were talking about before the break? Wow.
I watched the videos. We should probably
We got past subroutines though, right?
We got past the control structure of subroutines, but we have not started on local variables or parameters, which is kind of a big topic of subroutines. Okay, but we'll finish this one first, and then we'll move on to subroutines again. All right, and here's the row sheet of today. All right. Okay, so here's the algorithm, and how many people made that one little tweak to the program and see what it does, like removing the +1 on line 6 or removing the -1 on line 8. Nobody has done that? Okay, you should try that. I mean, because it does change the program just ever so slightly, but the behavior of the program just gets changed completely. Okay. All right, so let's go ahead and get started with this homework assignment. I'll give you the solution today.
The recorder run?
The recorder is running. Yes, it is running. But that itself by itself is not enough, because you have to make sure that I'm recording actually my voice, because otherwise you can be watching a silent movie.
Which would be enough for a trade?
Well, depends on the class. For some classes, yes, watching a silent movie would just be fine, but for classes like this, maybe an explanation is good too. All right. So let's go ahead and get started with the first test case on sheet 2. And just to fit everything on the screen, I'm going to have to reduce the size just a little bit so I can show you both the code and also the trace at the same time. Okay, this is good enough. I'm just covering a part of the then, which is not going to be a big problem. Okay, so we start with line 1. Line 1 is pretty easy. B gets initialized to 0. Line 2, E gets initialized to bar A bar -1. Bar A bar is the number of elements in an array. In this case, we have 4 elements. So 4 minus 1 is 3. E gets initialized to 3. We don't track line 3 because line 3 has no real purpose other than marking the beginning of a loop. So we go to line 4. Line 4 is going to update M by using the floor function. The floor function is taking the largest integer that is less than or equal to whatever is inside the parentheses. In this case, B is 0, E is 3, 0 plus 3 is 3, 3 divided by 2 is 1.5. The largest integer that is still less than or equal to 1.5 is 1 itself, so that means M is 1. Then we move on to line 5. Line 5 is the beginning of a conditional statement, a multi-branch conditional statement. So we have to say A bracket M is less than K is either true or false. In this case, M is 1, so A bracket M is referring to A bracket 1. A bracket 1 has a value of exactly 3. 3 is less than K. K is also 3, is false. Okay. Since this is a multi-branch conditional statement, we have to go to the second branch to see whether that condition is true. A bracket M is once again 3. 3 is greater than 3 is also false. And there's nothing else to do because we don't have an else to catch everything else. So we get out of the conditional statement onto line 10. Line 10 has to determine whether it is time to exit or not. The first condition is A bracket M equals K. and that is true already. And since since this is going to use short-circuit evaluation, this is all that I need. The second part of the disjunction is not needed because the first part is true already, and the two parts are combined using a disjunction, which means as soon as I know one side is true, I don't need the other side. Yep.
So do we have to do short-circuit evaluation?
I did not say specifically that you have to show short-circuit evaluation, so in this case, I'm not going to take points off if you do not just stop here. So if you say the entire thing is true, that's okay. Also, in this case, it doesn't matter whether it's short-circuit or not, because you're not going to get, you will not access an element out of index or index range in this case regardless. So it's going to be okay either way. But I just want to be consistent, in my notes here. And once we get out of the loop, we have to move on to line 11. Line 11 seems a little bit confusing, but it really is just a normal conditional statement. You update the left-hand side with whatever the value is for the right-hand side. The right-hand side in this case is a bracket m equals k, which is true. Okay, so found becomes true. Oh, I was scrolling using the wrong screen. So found gets true, and we're done. Are there any questions about the trace of the first test case? Yep, go ahead.
When I was doing it, for some reason I didn't see the found column, but I put it in comments for lines where you left that it was true.
Okay, well, I'll take a look and see how you represent it.
Okay.
All right, so that's the first one. Second one, pretty much the same thing, except we are looking for -6 in this case. So we start with line 1 again. B gets initialized to 0. On line 2, E gets initialized to 3. Then we go to line 4. M gets a value of 1. This part is the same as the previous one. And then we go to line 5. Line 5 is starting to be a little bit different. A bracket M is A bracket 1, which has a value of 3. 3 is less than -6. Whoops. K is -6 is false. So we have to move on to line 7. A bracket M, which is 3, is greater than K, which is -6, is true in this case. We move on to line 8. Line 8 is going to update E using the value of M minus 1. M is 1, 1 minus 1 is 0, so E now gets a value of 0. Then we get out of the conditional statement, we move on to line 10. Line 10 has to evaluate these conditions. A bracket M is still A bracket 1, because M is still 1. A bracket 1 is 3. 3 is the same as -6 is false. Okay? So in this case, I have no choice but to evaluate the other side, which is B is greater than E, which is also false. False or false is false, which means where do we go next? We have to go back to line 4. Okay? So we go back to line 4, and we are going to recompute M in this case. This one is easy. 0 plus 0 is 0. 0 divided by 2 is 0. The floor of 0 is also 0. We move on to line 5. A bracket M is less than K is -5 is less than -6 is false. Okay. So we move on to line 7. A bracket M, which is -5, is greater than K, which is -6, is true. So now we go to line 8 again. Line 8 is going to evaluate M minus 1. M is 0 already, so that means M minus 1 is -1. We will update E with -1. Then we get out of the conditional statement onto line 10. A bracket M equals K is false. B is greater than E is true, so the entire expression is true. After we get out of the loop, we have to continue onto line 11. Line 11 is going to update file using the value of A bracket M equals K. M is 0. A bracket M is A bracket 0, which is -5. -5 equals -6 is false. Okay? So we have to say false here, and then put a post. That's the end of this particular trace. Are there any questions about this trace? No questions? Okay. Moving on to this one here. This one, I'll just go a little bit faster this time. Okay. E gets initialized to 0, E gets initialized to 3. The first part is identical. M gets initialized to 1. So in this case, K is 7. Sorry? Oh, okay. So A bracket M is A bracket 1, which is 3. 3 is less than K, which is 7, is true. So we move on to line 6. Line 6 is going to update B with M plus 1. M is 1, 1 plus 1 is 2, so B is now 2. Then we move on, then we get out of the conditional statement onto line 10. A bracket M equals K is false because we just did the comparison, it was less than it. And that's all that we need to continue with the loop. Back to line 4. So line 4 this time, sorry?
False. So you need to evaluate the other
Oh,
statement.
that's right. Okay, sorry. That part is false. The other part is false as well, so the entire thing is false. That's why we're going back. So getting back to onto line 4. Line 4 is B plus E divided by 2, and then we take the floor of that. B is 2, E is 3. The sum is 5. 5 divided by 2 is 2.5. The largest integer that is less than or equal to 2.5 is 2. So M gets updated to a value of 2. We go to line 5. A bracket M is less than K is, well, let's take a look at A bracket 2. It is 10. 10 is less than 7 is false. Then we go to line 7. A bracket M is greater than K is true because 10 is greater than 7. We go to line 8. This time we update E. We update E to be M minus 1. M is 2. 2 minus 1 is 1. So E gets a value of 1. Then we get out of the conditional statement onto line 10. Line 10 will first test whether A bracket M equals K. That is not true because 10 does not equal to 7. We evaluate the second condition, which is B is greater than E. That one is true because B is 1, B is 2, E is 1. So the second condition is true, so that makes the entire conjunction true. We get out of the loop, moving on to line 11, and then we have the update found with A bracket M equals K. M is 2, A bracket M is 10. 10 equals to 7 is false. So this one ends up with a value of 4, false, and we are done. Are we still doing okay so far with this code? Okay. Yep, go ahead.
When we're writing actual code, can we split line 10 into 2 lines as long as it's followed by a semicolon?
Yes.
Okay.
You're talking about, when you're actually writing C or C++ or PHP actual code, yes, you can split a line into 2 anywhere in a C program. Because for the most part, with a C or C++ program, the line feed character, which separates a line into 2, is really considered the same as a space. So you can basically break this entire program up into like tons of lines, and it will still be considered the same to the compiler. Or you can combine all the lines into one line, and it will still be considered as one single. The structure of the program will still be the same. The only programming language where line feed or new line is important or significant is Python. So as long as you're not programming in Python, you can put a space just about anywhere without changing the meaning of the program. Okay. All right. So we're moving on to the last one, sheet 5. I think this one has a value that is greater than everything. Yep, we're looking for 12. So just to make this really quick, line 4. This one is actually true because k is larger than all the values in the array. So this one is true. We go to line 6. We update b to 1 plus 1, which is 2. We exit the loop. We go to line 10. A bracket m equals k is false. B is greater than e is also false. So the entire expression is false. We go back to line 4. 2 plus 3 is 2.5. The floor of that is 2. We go to line 5. This condition is true again because k is larger than all the values in the array. We go to line 6. This becomes 3. We go to line 10. A bracket m equals k is false. B is greater than e is also false. So the entire expression is false again. We go back to line 4 one last time. This time is 3 plus 3, which is 6. 6 divided by 2 is 3. The floor of that is also 3. We go to line 5 again. That condition is still true because k is larger than all the elements in the array. Moving on to line 6. The beginning is now 4. We exit the conditional statement. Go to line 10. A bracket m equals k is still false, but b is greater than e is true. So the entire expression is true. We get out of the loop. We end up on line 11. And a bracket m is a bracket 3, which is 11. 11 equals to k, which is 12, is false. So that becomes the value in the variable found. And we are done. All right. Any questions about the trace? Questions? Okay. Save this. And we are done. And now we're moving on to local variables and parameters. Now, local variables and parameters is actually a pretty big topic. Let me see if I have any alternative in this case. Yeah, so you might want to use the updated notes instead of this one because they are really the same. They have the same information, but the presentation is a little bit different. So I would use the new notes here. We have already covered section 2 and section 3. So now we are moving on to section 4. And hopefully today we'll get to section 5, but we may or may not be able to get to section 5. Okay, so before we talk about what is a local variable, I have to make sure that we understand that every variable that we have used up to this point in this class, they are all global variables. And global variables, as the name implies, means that a variable is accessible anywhere within your program. Inside a subroutine, outside of a subroutine, on line 1, on the last line, a variable is just always there. We're doing okay so far with that concept. Okay? A local variable, on the other hand, is local in 2 senses, not just 1, but 2. Okay, so we'll go ahead and click on that note, and so we know where this stuff is coming from. So here, a local variable is local in 2 senses. It is local in the sense of it is scope-wise, it is local, and it is also local in the sense that it does not even exist until the subroutine, including the local variable, is invoked. Okay, so we'll go ahead and take a look at the sample program. We'll take a look at the program that is quote-unquote broken, and then we'll take a look at a fix to fix this particular program. All right, so what I'll do is I'm going to print, make a very simple program here. Defines x2 times 2 basically. And instead of using times 2, we'll do it the long way. So we'll just say I gets 0, while I is less than 2, do a particular number x gets x plus okay, we'll change this to x4 times 4. I gets I plus 1, and while, and define sum. Okay, fix the indentations. So now we have a very simple loop here. Doesn't do a whole lot. All it does is to multiply a number by 4. It does that by doubling x twice. If you double x once, it is times 2. If you double x twice, then it's times 4. Is that okay so far? Okay. In fact, we can trace this code with a single variable x, just to make sure that this code works. Okay. Let's go ahead and do that. I'm going to write a. Okay. I'll save this program again, when I'm done with it. Okay. So we'll initialize x by 1, invoke x4, and see what happens to x. Let's make it a little more interesting. Make it 3. All right. So we'll trace this program once first, just to make sure the subroutine itself does not have a problem. Comments, because we do have one condition to evaluate on line 3, line number, and x is a global variable, so is I. So they exist from the very beginning of the entire program execution, and line number is just both of these columns, A and B, do not get represented when the program is actually executing. So in other words, columns A and B are only useful when we are tracing a program. They do not actually consume space when you're executing a program in RAM. The precondition is we don't need to know anything about X or I because they will both get initialized. On line 8, which is the first line outside of the definition of a subroutine, X gets initialized to 3. On line 9, we invoke x4. When we invoke a subroutine, there are 2 things to do. One is to allocate the leftmost available column and label it return line number so that we can remember when the subroutine is done, where am I supposed to go? In this case, where am I supposed to go when the subroutine is done? What is the line next to line 9? Post. Okay, we're done basically. When the subroutine is done, we return to post, which means we're all done. The second thing that you do when you invoke a subroutine is to start execution at the beginning of the subroutine that you are invoking. In this case, that's line 2, because line 2 is the first line inside the subroutine x4. Line 2 is initializing I to 0. Then we move on to line 3. We evaluate the condition I is less than 2. That is true because 0 is less than 2. We go to line 4. X gets doubled, which means that x becomes 6 in this case. We go to line 5, we add 1 to I becomes 1. Then we go back to line 3 because this is a loop. We reevaluate the condition. I is 1, 1 is less than 2 is still true. We move on to line 4, we double x, so it goes from 6 to 12. We go to line 5, we add 1 to I goes from 1 to 2. We go back to line 3. I, which is now 2. 2 is less than 2 is false. We get out of the loop. On to line 7. Now line 7 marks the end of the invocation of a subroutine. Once again, there are 2 things to do. The first thing you have to do is to find the rightmost return line number that is still active, that is not deallocated. In this case, we only have 1, which is column E. Column E tells us that we have to go back to post. So that's what you do, is to remember you have to go back to post. But as soon as you do that, you also have to remember that this return line number is not in use anymore. So we have to deallocate this column. To deallocate a column, we just have to annotate it accordingly. By, in this case, I'm using font effect of striking out. So this basically marks, at this point, column E is no longer in use. And we are getting back to post, and this is the end of this execution, the execution of this program. Yep.
I just had a quick question about I being a global variable. It's still global even though it's only used in the subroutine?
Yes, because I did not indicate any otherwise. Yep.
I have a question.
So in pseudocode in this class, if I don't say something is local, it means it's automatically global. Yep. Yep.
I have a small question related to the program. Is there something that we could do besides using font effects? Because it seems like that takes an unnecessary amount of time.
You can probably associate that with a hotkey, so you can just press Control X. Well, Control X is used for something cut, right? So you can use Control something to do a strike through. You can program the shortcut keys if you want to. But in the class, I'd like to do this because it clearly indicates at which point are we deallocating a particular column. Okay. Any other questions about this trace? Yep.
For the local variable I, we don't really know. Looking at the pseudocode, we don't know when the column for I was created, do we?
Because it is a global variable, it always exists. In other words, as soon as you start the execution of this program, X and I have columns allocated. It's just that when you first start the execution of this program, or right before on row 2 of the trace, they are there already. We just don't know what their values are. Okay?
They were created from.
They were created from the very beginning of the execution of this code, and they exist. They keep existing until the very end of this program.
That's true for the compiler creates it.
Yes.
In C.
For global variables in C and C++, they behave exactly the same way. They exist as soon as you start to execute the program, and they stay there until the very end, right before you exit the program. Okay. In other words, they live as long as the program itself, and they are visible everywhere within the program.
So that's global?
That's global, yep. All right, so are we still doing okay so far with this program? I'm going to save this program and give it a name of X4, and we know this code is correct, okay? Even though I have not used the pre and post condition to prove that it is correct, we know that it is correct at this point. All right, so let's go ahead and change the program a little bit. This time I will save it using a different name, so save as, and this time I will say multiply by 16, but it is the incorrect version of doing it. All right. Now, since I know how to do multiply by 4, multiply by 16 should be pretty easy, okay? Because I can just basically repeat the same code here. So I just copy and paste this part. Except here, I don't just double. I can invoke the other subroutine. Extend the line numbers a little bit. All right. So on the surface, this should work, right? Because if I quadruple something twice, it should be the same as multiplying that number by 16. Because 4 squared is 16. Are we doing okay so far with that logic? Except this program is not going to do that. Okay. And we'll go ahead and do the same thing as last time. X gets a value of 3. 16 times 3 should be 48. So by the time we get to post, the value of X should become 48. And I would invoke times 16. And we have line 16 and 17 here. All right.
Do you still need line 8 in there?
Line 8. Oh, I didn't see it. Well, let's see what this program will do. I'm just going to leave it there just so that you can see what this, because we're interleaving the actual main program with the definition of subroutines, which you cannot do in C. But you can do this in some other programming languages. Like Perl, PHP, they all let you do something weird like this. That's because they're all scripting languages. They're very flexible. Very flexible, yeah. Okay, so in this case, what is the first line that is outside of the definition of a subroutine? It's line 8, okay? Line 8 is, in fact, the first line outside of the definition of a subroutine. So we start with line 8. Line 8 is going to give X a value of 3. What is the next line that is outside of the definition of a subroutine? Line 16, that's right. This is exactly what a Perl script will do. Same thing with a PHP script. You can interleave, the main, the quote-unquote main part of your program by subroutine definitions, but you cannot do that in C and C++. Okay. All right. On line 16, it's going to be the same thing because I just replicated that line. All right. So on line 17, nothing really new here. We are invoking a subroutine. Two things to do: allocate the leftmost available column for the return line number. There's nothing to return to except for the end of the program, so the return line number is post. Then we start with the first line of the subroutine that we're invoking, which is on line 10 in this case. I gets initialized to 0. Everything seems okay. I mean, pretty much the same stuff as last time. I is less than 2 is true. And then on line 12, we invoke another subroutine, which is x4. We allocate the leftmost available column, which is not E anymore because E is now currently in use. So it's column F. We call that return line number. And in this case, when we are done with the invocation on line 12, we have to continue execution on line 13. So the return line number is line 13. Then we continue execution on the first line of the subroutine, which is line 2. Just going to line up the column a little bit here. Are we still doing okay so far? Okay, everything up to this point should be kind of boring because it's really a lot of repetition of stuff that we have done already. On line 2, I gets initialized to 0. Now, at this point, I think some people are starting to notice like, I'm not sure about this program because we are reinitializing the very same variable that is used in x16, but we are now in x4. That may cause problems. But some other people may think, but that's okay because we are reinitializing the same thing with the same value, so it's not really doing any harm. Okay? So we'll continue with this program, but I think we should have a little doubt at this point and say this program doesn't seem to be right because it's reusing the same variable I at 2 different places. Okay, line 3, I is less than 2 is true. Now remember, when we trace line 11, it's using I of column D. When we evaluate the condition on row 12, which is line 3 in the program, we are using the very same column D. Okay. But in this case, they're the same value, so if they're both true, which is both conditions are true, which is okay. On line 4, we double the value of x. 3 goes to 3 becomes 6, and then on line 5 we bump up the value by 1. Oh, okay. Now we are starting to have some serious doubts here, because this is the very same I that is used by x16. So, what is this program going to do when we are messing up the same variable that x16 is using? Well, let's finish this part first, and then we'll go back to that part. After line 5, we go back to line 3. I is less than 2 is still true. We go to line 4. 6 gets doubled again to 12. We go to line 5. I gets incremented to 2. We go back to line 3. I is less than 2 is false, because 2 is less than 2 is not true. Then we get to the end of this subroutine on line 7. We locate the rightmost active return line number. It tells us we have to continue execution on line 13, and then this column is now deallocated. Okay, so copy, paste, and strike through. Now we are on line 13. Line 13 says, well, let's add 1 to I again. Well, I is already 2. Adding 1 to 2 makes it 3. After line 13, we have to go back to the beginning of this particular loop on line 11. And guess what? I is less than 2 is now false. Do you guys see what happened here? Okay. So the program will exit. It's not going to crash, but it does invoke x4 1 time too few. Okay, it's not enough. Okay, just to finish this program, we'll go ahead and indicate that we get to line 15 at this point, and it will look up this return line number because this one is already gone. So this becomes our rightmost in use return line number. It tells us we have to go back to post, and then we can deallocate this column, and that's the end of this trace. But it is incorrect because we're supposed to double 12 one more time, or multiply it by 4 one more time, and this time it did not. What is the source of this problem? Why is this program not behaving? Yep.
We used the same variable because it wasn't the same global variable. We weren't able to check if it had gone through the program correctly.
Exactly, because I'm using the very same variable to keep track of how many times I have to go through a loop in x16 and in x4. Okay, now x16 is the first one because it's the first subroutine to get invoked. But by the time we get to x4, it's going to clobber, it's going to corrupt the variable that we were relying on in x16, and that's why the program is not doing what it is supposed to. Yep.
But you initialized it to 0, so shouldn't that eliminate the corrupted part of the x16 subroutine?
Yeah, but when you continue execution, it just bumps it up by 1, so it becomes 3. So you don't even have a chance to go back to invoke x4 again in the supposedly second iteration of the loop. Okay, you invoke it once and then you get out of the loop already. Okay, so this is incorrect. We don't want the program to behave this way. How do we fix this program? Well, there are several ways to fix this program. The easiest way is to say, well, I can see the problem being, just having one variable to control 2 loops. So why don't we use j or another variable name for one of these loops and be done with it, right? I mean, that's a pretty easy fix. You can always go to, just pick one of the 2. Okay, I'm just using this as an example. So go to this little block of code here. Whenever we mention I, change that to j. That will fix the program, okay? But how extendable is this approach? With 2 subroutines, it's okay. With 3, it's okay. How many subroutines do you think a really useful commercial program has? A lot, okay? So how can you make sure that the variable name that you use is not used somewhere else by another subroutine? It's kind of hard, but I'm smart. I know how to do this. Yep, go ahead.
Arrays?
Arrays? No, you don't need to use arrays here. Okay. But I have a really smart idea. Go ahead.
You can assign variables to the subroutine itself, right? Like, so you can make it so that the subroutine, the variables inside the subroutine are only specific to the subroutine and not to the
Right.
entire
We're
program.
trying to do that. We're trying to localize the use of variables. But I have an easy way to fix this program, make it scalable, and yet not use local variables at all. I'll just prefix the name of a variable with the subroutine that it belongs to. In other words, with this selected block of code, I'll just prefix I with x16i. So everywhere you see I here, it is x16i, and I'll do the same thing consistently throughout the program. From here to here, whenever you see I, I'll change it to x4i. Okay. So now, even if I have 3,000, subroutines, I can just use the suffix idea to make all the quote-unquote I variables unique to that particular subroutine. But what if I have a typo? Whoops. Remember, a global variable is global, which means it is visible anywhere within the program. So if I have a typo because I copy and paste my code and forgot to change one reference to a variable, do you think the compiler can catch that and go like, you know what, this variable's name doesn't seem to belong in this particular subroutine? Nope, it doesn't do that. So your program is going to compile just fine. But when you run it, it's not going to run just fine. Okay? And there are programs that are not going to run, have problems, and then there are programs with problems that are difficult to locate and fix. And having one subroutine to clobber the variables of another subroutine is one of those things where it's really hard to fix. Okay, it's really hard to locate the problem. Once you locate it, it's easier to fix. Okay, so that approach is not going to be scalable. Even though you can use it, it's not scalable. So that's why we're going to have to introduce the concept of a local variable. So let me save the program again, and this time using local variables, so it will be the correct version, okay? So I'll use, say, local, and it is correct. Syntactically, it's a very simple change. Syntactically, all I'm going to do is to say, you know what, at this point, I have a local variable I. In other words, for local variables, I have to make it explicit and say, this variable is local. I. So syntactically, the change is tiny. Okay, it doesn't really make that much of a difference. Okay, just renumber the lines. Okay. Yep.
So it has to be made local inside the subroutine.
Sorry?
When you tell the program that it's local, it has to be made local inside the subroutine.
That is correct.
Okay.
Now this approach is really, I borrowed this concept from Perl and PHP. So in Perl and PHP, if you want to use a local variable inside a subroutine, you have to say my and then the name of the variable, and that makes it local to the subroutine. If you just start to use a variable in Perl and PHP, it automatically becomes a global variable. In other words, the rules that I described in this class, a part of that is borrowed from C and C++. The other part I borrow from PHP and Perl. Yep.
So what about C-based languages?
In C, you always have to declare a variable before you can use it. So you basically will have the equivalence of global I, somewhere in the program to make a variable global.
So what about for subroutines though? How do you make the local in C?
It's about the same thing as what we described here, except you don't specify local.
Oh, I get it. So if the
You just say variable I.
Yeah, if the variable exists inside the subroutine, but it doesn't exist if it wasn't declared prior to the subroutine. Then
Right.
it's local.
C and C++ require declaration before you use a variable, whether it's global or not. But in most scripting languages, you do not need to declare global variables before you use them. The first time you use something that is not already existing, it automatically creates it as a global variable. Okay, so syntactically speaking, this program is really simple, but let's just take a look at the meaning of I in this case. Now, if I say that I is a local variable, that means this particular variable is only visible from here to here. That is the scope of a variable. Okay, in which part of the program is it visible? Well, it's only from line 2 to line 7 for this particular variable I. For this particular variable I, this is its scope from line 11 to line 16. What that means is when you are in here, you cannot see this variable I. When you're in here, you cannot see this variable I. Is that okay so far? That's really just the scope, which is just looking at the definition of I, you can figure out which part of the program has visibility of that particular variable I. But when we, sorry?
There's two different instances of the same variable.
It is not the same variable. They just happen to have the same name.
Same name.
Right. They have the same name, but they are not the same variable. But the second part of a local variable is, well, let's look at the trace. That would explain everything that I wanted to explain. So we'll go ahead and reuse the same spreadsheet, but this time I'm going to delete this column. In other words, because I is not a global variable anymore, I don't even allocate any columns for it until I need it. Okay, so this is a very, very important aspect of a local variable is it doesn't even get allocated until the subroutine containing it is invoked. Are we doing that okay so far? Yep.
You also need initialize too, right? Allocated and initialize.
Right. Well, allocating a local variable does not include initialization. So as we'll see later on, how I represent that a local variable is always uninitialized. Okay. Let's go ahead and get started with this program. So because of that stupid mistake, I still have line 9, being the first line outside of the definition of a subroutine. Okay, I didn't fix that, but that's not important. This part is important. When we invoke x16, we'll do exactly the same thing as last time. Okay, Two things to do. The first thing is to allocate the leftmost available column, label it return line number. In this case, there are no additional lines to return to, so the return line number is post. But there's one extra thing to do now. Okay, as you are allocating columns, okay, for the return line number, you also have to allocate for local variables. So in this case, I'm going to take up column E for local variable I of x16. And all local variables start with unknown values, so it is very important to mark column E with a question mark to indicate this local variable starts with an unknown value. Now that is a very, very important programming concept in C and C++, because you cannot count on I, a local variable, to start with any specific value, just like with global variables. Okay? If you forget this thing and you start to use the value of I in an actual C or C program, the compiler usually won't give you any warning unless you ask the compiler to nag. And yes, you can ask the compiler to nag. Yep. You always want to make your tool nag as much as it can, because everything that it warns you about probably has a good reason to warn you about. Okay, so now that we are done with these two things, we continue execution inside the subroutine, starting on line 12. Line 11 doesn't really do anything, because all it does is to say, yes, this subroutine has a local variable I, but it really doesn't do anything. So we start with line 12. Line 12 is initializing I to 0, but this time, because I is column E, it is column E that gets a value of 0. Well, so far it's a little bit different from last time, but we'll see how this one is different when we get to subroutine X4. Yep.
So, line 11, we basically did what line 11 does when we gave assigned our red line. We basically did what line 11, because we're saying that I is local at that point.
Line 11 really does not allocate column E. It's really just telling the compiler that when you invoke the subroutine, column E should be allocated. In other words, it's the invocation that is allocating column E. It is not line 11.
So it's like at that point. So at the invocation point is when it's actually declaring the variable, and then at line 11, it's telling the compiler that this variable is local.
Right.
Okay.
Yep. On line 12, we initialize, that's okay. On line 13, pretty much business as usual as last time. This is true. And then on line 14, we invoke X4. Now this time, we'll do exactly the same thing. Okay. We first allocate a column for return line number. In this case, we are returning to line 15. So that part we know for already. But we also have to allocate for any local variable within X4. So that means we look at line 2 and go, oh, okay, we do have a local variable I in X4, so now we have to allocate one additional column for that local variable I, which is now using column G. And you can see that the two quote-unquote variable I's are different. One is using column E and is only visible from line 11 to line 16. The other one in column G is only visible from line 2 to line 7. Okay, so now that we are continuing execution on line 3. Line 3 really has no visibility of column E anymore, because the scope dictates that the local variable of X4, the scope dictates that this local variable I is only visible within this portion. Now that my execution point has exceeded or has gone outside of that range, we have no visibility of I anymore on column E. So now that we are on to line 3, we initialize the other I to 0. Are we doing okay so far with this code? Yep.
Is there any representation that we need to do to show that I is visible, or we just know it? Do you know what I'm saying?
We just know it, because we are not within the visible range of that variable I.
So when the next red line actually kind of tells you that I is no longer visible.
We just kind of have to track it by hand in this class.
Okay.
In an actual programming language like C and C++, the compiler will enforce that. So here comes line 4. Pretty much, same thing. Line 4 is just checking the condition. Line 5 is doubling the value of x. Line 6 will add 1 to I. Which I am I adding 1 to? The one in column
G. One column G.
in column G. That's right. So this is significantly different from last time, because last time we were clobbering the same column, over and over again. This time it is very clear that x4 has its own column G and x16 has its own column E. Go back to line 4, x is less than 2 is true. Go back to line 5, doubling the value of x to 12. Go to line 6, adding 1 to I, which is column G. Go back to line 4, I is less than 2 is false. And then we get out of the loop. We continue execution on line 8. Now this time line 8 has several things to do. It's just like last time, it has to look up the rightmost active return line number, which is line 15. And remember that we have to continue execution on line 15. But when it's time to deallocate columns, now it has 2 columns to deallocate. Not just one, but both of these columns have to be deallocated. In other words, whatever you allocate for the invocation of a subroutine, you also have to deallocate at the end of the execution of that subroutine.
That was my question, I guess. Got ahead of you, sorry.
Okay, that's fine. But it answer your question?
Yes.
Okay. Very
So
good.
when you end the subroutine, the variable has to be deallocated.
Correct.
Okay.
In other words, a local variable is associated with not the subroutine itself, but an invocation of the subroutine. So you can have 20,000 subroutines, defined, and if they only have local variables and none of them is invoked, then you have no storage allocated for any of the local variables.
In a compiler, is that enforced, or do you have to do that inside the language itself?
The compiler does that.
Okay.
Because this is the specified behavior of local variables.
So this is the logic, and the compiler will do it itself.
That is correct.
Okay.
C automatically understands how to handle local variables like this, and PHP, Perl, Java, they all behave the same way. Same thing with Visual Basic. Basically all modern programming languages behave like this. So are there any questions at this point?
I have a non-sequitur question.
Go ahead.
You mentioned the compiler a lot through this. How much, percentage-wise, work does the compiler do?
That's a good question. Let me just save this program first, and I'll show you how this code works, okay? So in other words, instead of just showing you the pseudocode and you guys go like, oh, okay, this is how it works, let's go ahead and write this program in C, just so that you can connect, pseudocode in this class with actual C code that you will definitely see in cisp300. So we'll go ahead and use a terminal for this. Go to today's folder so we can save it. And I'll go ahead and write this program in C. I'll just call it x16C. Okay, there are several things that you normally don't have to do, so don't mind that portion. So this is all stuff that's kind of, specific to C. Okay. To define a subroutine in C, you basically have to do something like this. So the syntax is not even important in this case. The open curly brace and close curly brace in this case basically marks the beginning of define sub and end define sub. And then whatever I put inside is int I. That is the declaration of local variable I in C. And in C, you cannot just say, I want to use a variable I. You also have to specify what is the type of the variable, which in this class we have not really gotten into yet. Okay. But that's the declaration of local variable I. I gets 0 is I equals to 0, because we don't use the left arrow symbol in C, which makes it kind of confusing at times. While I is less than 2, do the following. And once again, I use open curly brace and close curly brace to mark the beginning and the close of the body of the loop. And in this case, the body of the loop has x gets x plus x, and I get I plus 1. And as I said a little bit earlier, in C, you have to declare any variable. In this case, x is a global variable, so it has to be declared outside of the definition of a subroutine. And then we have x16, pretty much the same thing. The void is basically just saying it does not return anything and has no parameter. We'll talk about parameters later. And it has its own local variable I. I gets 0, same thing, while I is less than 2. In C, you don't have to spell invoke. If you just say x4 open paren and close paren, that is the same thing as invoking the subroutine x4. I gets I plus 1. So that's how you write, basically x4 and x16 in C. What do you think? I think C is sometimes more cryptic, even though it is terse. You don't have to type as much, but it is definitely sometimes more cryptic. All right. So where do we put the rest of the program? In main. Okay. So this is a very kind of strange idea in C. Is you don't really have anything that can start execution. The entry point of your entire program is called the main subroutine. In other words, you cannot specify any code outside of the definition of a subroutine. Okay, every code, every statement, they have to go to a particular subroutine. So how do you get started with the entire program? Well, they predefine this name main to be special. Okay, that's the entry point of your C and C++ program. In other words, you can kind of see that there's a hidden invoke main somewhere that you cannot see. So whatever you specify in main is the starting point of this program. So in this case, the starting point of this program, so I just put x gets 3 into here and invoke x16, and that's the end of this program. But the output of this program is not visible. Okay, so instead of using printf, which was my original intent, I'm changing that idea because I want to show you guys how to use a debugger. All right, so at this point we have created a text file called x16.c. It's a regular text file. If you're using Windows, you can use Notepad to create this file because it really is just a regular text file. To get this file to become an executable, at least in this case, I use a compiler called GCC, which stands for the GNU C compiler. And we'll specify the output, which is the executable of the same name. And then the source code is x16.c. And this is the compiler actually at work converting or translating the .c code, which is in plain text, into a binary form where the processor can execute. Because the processor can only execute instructions that are specified in long strings of zeros and ones. And you certainly don't want to program in those long strings of zeros and ones. But the compiler does not understand, the processor does not understand while, if, and all those other things. So someone has to be doing the translation. In this case, it's the C compiler.
That's assembly language.
Sorry?
Assembly language.
Assembly language, it still requires conversion or translation. It's just a whole lot easier to translate. I forgot one thing. I forgot to specify a -G. A -G means I want to include debug information. Now, this is the part where most instructors do not talk about, but they really should, is the use of a debugger. GDB is the name of what we call a debugger. A debugger, as the name implies, is a tool for debugging a program, which means you want to find out why a program is not working the way it's supposed to. But you can also use it to trace a program, trace the execution of a program step by step. So in this case, we can single step the program. Okay, it won't let me do that. So we'll put a breakpoint on line 31 first. Now remember, this part you don't have to remember. This is all really for future reference. Okay, so I'm now on line 31. It's going to change x to 3. We single step. Now we're in x16 on line 21. So for the most part, you can do single stepping or tracing a program kind of the same way that we do in this class, except it's not displaying everything in a big spreadsheet, and you cannot really track the value of variables. If you want to know what I is, you have to say print I. It currently has a value of 0. So single step, single step, single step, single step. You print the value of I again. It is still 0, but this time it's a different I. I is now 1, and so on. Okay? So tracing this program is going to take a little bit of time. I'm going to shortcut the whole thing, put a breakpoint on line 33, which is the end of the main subroutine, which also means post from our perspective. So we just continue executing the program until we get to that point. And at this point, I want to print x, because what do you think should be the value of x?
48.
We should have multiplied 3 by 16. So x should have a value of 48. So let's double check. It does have a value of 48. Okay. So this is pretty much as close as you can get with tracing when you're actually dealing with a real C program. It has its advantages, which is not being tedious like what we do in this class, but it also has a disadvantage of not being to visualize the change of the variables. And certainly you cannot go back in time. If you forget to print the value of a variable at a certain point, you cannot go back and say, oh, I want to backtrack this program a few lines and find out what is the value of a variable. You cannot do that.
You can't backtrace. You can't backtrace.
You cannot backtrace, but what you can do is to trace the value of a variable. So every single time you stop or you just single step the program, it prints the value of a variable. It's still kind of much harder to read compared to the traces that we do in this class. Yep.
Do you like Visual Studio C++?
I don't use any visual tools.
Okay, that's enough answer.
But if for people who feel comfortable with a visual environment, it's not a bad thing to do, because if you want to find out what a variable is once the program has stopped execution, you just put your mouse pointer right on top of a variable, just hover, and it will print the value of a variable at that time.
Yes,
But once again, you can only see the current value. You cannot see how it got changed over time.
It has a nice debugging.
Basically the same thing. A GDB is just a very tedious and command line way of doing things.
Better in the long run, to learn it that way. Something like that.
I use this, for almost all of my debugging needs. I don't use visual tools too much. The nice thing about using this kind of tool is it does not require a full GUI to use it. In other words, if I just SSH or remotely, if I remote into a server, I can debug a program just as well as a program that I'm running on this computer. But if you use a visual environment, then you lose that ability to remotely go into a system and track down a program. All right. So this part is really just an illustration of how do you actually write a program in C and get it to work. I'm not really tempted to finish this entire program. Do you guys want me to finish the whole thing, or you kind of can figure out how this program is going to finish? I think this one is okay that I don't finish entirely, because I want to use the time to write another program, to illustrate how local variables are used in recursion. Okay? Because that's really a question that some people might have is, well, what about recursion? What if a subroutine is invoking itself? Then how many columns do I allocate, and how do we allocate columns? Because it's clear that when we have x16 invoking x4, then we have two columns, both named I. But what if I'm having a subroutine to invoke itself, right? Let's go ahead and write another subroutine. Another sample program to illustrate it. We'll just call this test, okay? And test has a local variable I. And let's see here. I gets the value of a global variable x. And I say if I I have to make this program somewhat useful too, so if I is less than 2, then x gets x minus 1, invoke test. Okay, we can do this. So we get x gets we wanted to exceed that at some point, and then we get x gets x times I. There you go. And if and define sub x gets the initial value of 1, invoke test. This is good. It's simple enough, and yet it will illustrate what a program like this will do. Recursion with local variables. All right, let's see the program first. And then we'll trace it. Okay. Usual stuff. And we do have one global variable. Which one is it? X. Yep. Because x is used outside of the context of a subroutine, so it has to be a global variable. So x is a global variable. It exists from the beginning of the execution of the program. And we'll say the precondition of x is unknown because we initialize it on line 10. And on line 11, we invoke the subroutine test. Allocate the return line number. And we return to post. Allocate another column for I. And as a variable that is, as a local variable, it is always starting with an unknown value. Okay. Then we continue execution inside the subroutine on line 3. Line 3 sets I should get a value of x. X has a value of 1, so I now has a value of 1. We go to line 4. I is 1, which is less than 2, so I is less than 2 is true. We continue execution on line 5. X gets x plus 1, so x is now 2. And then we move on to line 6. We invoke the very same subroutine. So what do you think we should do here? We're invoking the same subroutine. We go through exactly the very same thing that we did earlier, okay? We already know this part, okay? Allocating the return line number is we already know this part. The next line is line 7, so the return line number is line 7. This part we already know. But we also know that it's the same way. If the subroutine that you're invoking has a local variable, you have to allocate it when you are invoking the subroutine. It doesn't matter that you're in the very same subroutine. Every invocation is new, okay? So because this is a new invocation, we allocate another column for I, and it also starts with an unknown value to begin with. Are we doing okay so far in terms of this concept here? The allocation of a local variable is on a per invocation basis, not on a per subroutine basis. Is that okay? So that means if you have recursion, every invocation of that subroutine will allocate additional columns. Is that okay? That's a very, very important concept. So this starts with an unknown value. And then we start from the beginning of the entire subroutine, which is on line 3. I gets the value of x. X has a value of 2 at this point, so I is going to get a value of 2. Moving on to line 4, I is less than 2 is false in this case. So we skip the entire conditional statement all the way to line 9. Line 9 is n define sub. N define sub will do the usual thing. You look up the rightmost active return line number, so you know where to continue execution. We continue execution on line 7. and then we deallocate every single column that we allocate for that invocation. And we have to format, change it to strike out. Now that we are on line 7 says it wants to multiply x and I and store the product in x. This is x, this is I, 2 times 1 is 2. So we are actually just storing 2 back into column C in this case. And then we end the conditional statement, continuing execution on line 9. On line 9, which is the end of the subroutine, we do exactly the same thing as usual. We locate the rightmost active return line number, which is column D. It tells us to continue execution at post. And at the same time, we now have to deallocate both of these columns. I'm just going to copy and paste these two. And that's the end of this particular program. Are we still doing okay so far with the concept of local variables? So it doesn't matter whether you're invoking a subroutine from outside, from inside the subroutine, or inside the very same subroutine that you're invoking, it's still the very same mechanism. Okay? The allocation and deallocation of local variables is on a per invocation basis. Are we doing okay so far? Okay. All right. So we have enough time to get started with passing by value. Okay, so we're moving on to parameters. Passing by value is not very different from local variables, with one exception. Okay, so what we'll do is I'll start a new program. This time we'll use a pass by value parameter. Okay, I'll just call this test here. And when we declare in this class, we declare a by value parameter. I'll just say by val and give it a particular name, by val v in this case. And we'll say x gets x plus v and define sub. And because x is a global variable, it has to start with a particular value. Let's say it starts with 2. And then we'll say invoke test. We'll say 4 goes to b. And that's my program. Okay, so we'll go ahead and trace it, save it first. We'll come back and talk about by value parameters again on Thursday, but I want to give you at least this much before we end today's class. All right, so let's trace this one. We don't need comments because we don't have any conditions to evaluate. There's line number and there's the global variable x. We start execution on the first line outside of the definition of a subroutine, which is on line 5. X gets a value of 2, and then we invoke the subroutine on line 6. This time it looks kind of funky, because when we invoke the subroutine test, we also have something that kind of looks like a reverse assignment statement, because but the direction of the arrow tells you which way you should evaluate it. Okay, what is updated by what? Okay. So let's start with the stuff that we already know. Because we're invoking a subroutine, we need a column for return line number. And in this case, any parameter that you're passing also require a column that you're allocating on a per invocation basis. So in this case, v as a parameter is also allocated on a per invocation basis. So that means we have to allocate v just like as if v is a local variable. Let's take care of return line number first. This is our last line, so there's nothing to return to except for post. Now, if v was a global variable, it would have started with an unknown value, with a question mark, right? As a by value parameter, it has a particular starting point. In other words, it starts with a specific value that is supplied by the invoke statement. So can anyone guess what I should type here with this little cell?
4.
4, exactly. So this is the only difference between a pass by value parameter as opposed to a local variable. A local variable is always starting with an unknown value, whereas a parameter starts with whatever value that the invoke statement itself specifies. Okay. Now that can come in very handy. Yep, go ahead.
Our pseudocode arrow there for the pass by value indicator, that's operator, that has a left hand side and a right hand side also.
Yeah, this one I use, I just use a right arrow. Yeah, because one to differentiate that this is not an assignment statement, and two, it still indicates which way information flows. All right. So once we get into the subroutine, there's only one line in the subroutine that does anything useful, which is line 3. Line 3 says we want to compute x plus v. X is global; it has a value of 2. V is a pass by value parameter; it has a value of 4. 2 plus 4 is 6, so x gets updated to 6. Now, other than the fact that the initial value of a by val parameter is specified by invoke statement, it has the same scoping rule. In other words, v in this case is only visible from line 2 to line 3. Okay, it's just like a local variable with a limited scope. It's also just like a local variable in the sense that it only lasts as long as the invocation itself. So now that we are done with line 3, we're moving on to line 4, the end of the subroutine. First thing is to look up the return line number so that we know we are done with this program. But the second thing is when you deallocate, you also have to deallocate the column for v, just like when v is a local variable. And that's why I said it really behaves exactly the same way as a local variable, with the exception that it starts with a known value supplied by the invoke statement. So do we have any questions about a by val parameter? The only reason why I want to kind of make sure that we get this through today is because of the close relationship between a local variable and a by val parameter. They are pretty much quote unquote the same thing, except one starts with an unknown value, the other one can use the invoke statement to give it a particular value. Yep.
So, for the syntax of this, when you deallocate the return line in the variable that is used inside the subroutine, you do it prior to posting. So like, because this one's so short, you don't do it on the post line, you do it on the line prior to posting. Because that's where you have the get the return line on line 4. So it's always the last line of the program where it gets deallocated. Or the last line of the subroutine.
The last line of a subroutine is the one that triggers the deallocation.
Okay. So that's where the deallocation would go for our purposes.
Yep.
Okay.
All right. There's a roll sheet. All right. I'll see you guys on Thursday.
What's your Android class number? The Android class number for the
362, CISP 362.
And then there's a follow-up class, right? 363.
With your 363 in spring.
Okay. So is it basically a 2-part then?
Yeah, it's kind of like a 2-part thing. I